Download this code from codegive.com, link in the description below. Symbol table, a comprehensive guide. A symbol table is a crucial data structure used in compilers, interpreters, and other language processing tools. It's essentially a dictionary that stores information about the identifiers, like variable names, function names, class names, etc., used in a program. This information is essential for semantic analysis, code generation, and debugging. Why do we need a symbol table? Consider the following simple code snippet in C. When a compiler processes this code, it needs to keep track of 1. Identifiers *x, y, add, a, b, result, main, printf. 2. Types *int, function. 3. Scope * where each identifier is valid, example a and b are only valid within the add function. 4. Values * the initial values assigned to x and y, and later the value assigned to result. 5. Memory location * where each variable is stored in memory, assigned by the compiler. 6. Function parameters * information about parameters passed to functions. 7. Return types * the data type returned by a function. Without a symbol table, the compiler would struggle to verify that identifiers are used correctly. Are variables used before they are declared? Are the correct number and types of arguments passed to functions? Resolve references * when add, x, y, is called, the compiler needs to find the definition of add and x and y. Allocate memory * the compiler needs to know the size of each variable to allocate the correct amount of memory. Generate code * the compiler uses the symbol table to generate instructions that access the correct memory locations and perform the necessary operations. Key concepts. 1. Identifiers * the names used to refer to entities in the program, variables, functions, classes, etc. 2. Attributes * the information associated with each identifier. Attributes vary depending on the type of identifier and the language. Common attributes include data type *int, float, string, array, etc. Scope where the identifier is valid. Storage class static, extern, auto, register, in C/C++. Memory address the location where the variable is stored in memory, often assigned during code generation. Value the current value of a variable. This is generally stored at runtime, but the symbol table might hold the initial value. Number of parameters for functions. Types of parameters for functions. Return type for functions. 3. Scope the region of a program where an identifier is visible and can be accessed. Common scope types include global scope identifiers declared outside any function or class. They are visible throughout the entire program. Local scope identifiers declared within a function or block of code. They are only visible within that function or block. Class scope identifiers declared within a class. They are accessible through the class name or an object of the class. 4. Nested scopes programming languages often allow scopes to be nested within each other. For example, a function might contain nested if statements or loops, each creating a new, smaller scope. The rules for resolving identifiers in nested scopes typically follow the closest definition principle. If an identifier is used within a nested scope, the compiler first looks for its definition within that scope. If it's not found, it looks in the enclosing scope, and so on, until it reaches the global scope. Data structures for symbol tables. Several data structures can be used to implement a symbol table. The choice of data structure depends on factors like the size of the program, the frequency of insertions and lookups, and the importance of efficiency. Here are some common options. 1. Arrays or lists asterisk. Asterisk simple implementation asterisk each entry in the array/list stores an identifier and its attributes. Asterisk lookup asterisk requires searching the array/list linearly. Time complexity, O, n, on average, where n is the number of entries. Asterisk insertion asterisk adding a new entry is relatively fast, O, 1, for an unsorted array/list, but O, n, if you need to maintain sorted order. Asterisk suitable for asterisk small programs with a limited number of identifiers. 2. Hash tables asterisk. Asterisk efficient lookup asterisk uses a hash function to map identifiers to indices in the table. Average case lookup time is O, 1. Asterisk collision handling asterisk handles cases where different identifiers hash to the same index using techniques like separate chaining, linked lists, or open addressing. Asterisk insertion asterisk also typically O, 1, on average. Asterisk requires a good hash function asterisk to minimize collisions and maintain efficiency. Asterisk suitable for asterisk most programs, especially when dealing with a large number of identifiers. 3. Binary search trees, BSTs. Asterisk ordered data asterisk stores identifiers in a sorted order based on their lexicographical value. Asterisk lookup asterisk uses a binary search algorithm, which has a time complexity of O, log n, on average for a balanced BST. Asterisk insertion/deletion asterisk also O, log n, on average. Asterisk balancing is important asterisk to prevent the tree from becoming skewed and degrading to O, n, performance. Balanced BSTs, example AVL trees, red-black trees, are often used. Asterisk suitable for asterisk applications where identifiers need to be stored in a sorted order. 4. Linked lists asterisk. Asterisk simple to implement asterisk each entry in the linked list stores an identifier and its attributes. Asterisk lookup asterisk requires searching the linked list linearly. Time complexity, O, n, on average, where n is the number of entries. Asterisk insertion asterisk adding a new entry is relatively fast, O, 1, at the head of the list. Asterisk suitable for asterisk symbol tables where there are frequently new identifiers and you always want to insert at the head of the list. Implementation example, Python with hash table. Here's a basic example of a symbol table implemented using a dictionary, which is a form of hash table, in Python. Explanation of the code asterisk. One symbol table class asterisk represents the symbol table itself. 2. Self.table asterisk a dictionary used as the hash table. The keys are identifiers, strings, and the values are dictionaries containing the attributes of each identifier. 3. Self.scope underscore stack asterisk a list used to keep track of nested scopes. When a new scope is entered, the current scope is pushed onto the stack. When a scope is exited, the previous scope is popped from the stack. 4. Self.current underscore scope asterisk a dictionary that represents the symbol table for the current scope. 5. Enter underscore scope asterisk creates a new scope. It saves the current scope to the scope underscore stack. 6. Exit underscore scope asterisk removes the current scope and restores the previous scope. It pops the saved previous scope from the scope underscore stack. 7. Insert identifier, attributes, asterisk adds a new identifier and its attributes to the symbol table for the current scope. It checks if the identifier already exists in the current scope to prevent redeclaration errors. If the identifier is already present in current scope, insertion is failed, and the function returns false, else true. 8. Lookup, identifier, asterisk searches for an identifier and returns its attributes. It searches through the scopes. It first checks if the identifier is present in the current scope, and if it's not, it checks the parent scopes. This searching is done by iterating backwards through scope_stack. If not found, return none. 9. Update, identifier, new underscore attributes, asterisk updates the attributes of an existing identifier. It first checks in the current scope and iterates upwards through the scope stack to find the identifier. If it can't find the identifier in any scope, it returns false. If found, attributes are updated and the method returns true. How it relates to a compiler. A compiler uses a symbol table during several phases. 1. Lexical analysis, scanning. The scanner identifies tokens in the source code, keywords, identifiers, operators, etc. Identifiers are added to the symbol table, if they are not already there, with minimal information, example just the identifier name and its type. 2. Parsing asterisk. The parser builds an abstract syntax tree, AST, from the tokens. The parser uses the symbol table to check if identifiers are declared before they are used. 3. Semantic analysis asterisk. The semantic analyzer performs type checking, scope resolution, and other semantic checks. It extensively uses the symbol table to verify that the program is semantically correct. This phase adds a lot of detail into the symbol table. The types of the variables are confirmed. If type conversion is possible, it is performed. 4. Intermediate code generation asterisk. The compiler generates intermediate code, example 3 address code, based on the AST and the information in the symbol table. The symbol table helps to map identifiers to memory locations. 5. Code optimization asterisk. The optimizer can use the symbol table to perform various optimizations, such as constant propagation, replacing variables with their constant values, and dead code elimination, removing code that is never executed. 6. Code generation asterisk. The code generator produces the final machine code. It uses the symbol table to determine the memory locations of variables and functions and to generate the appropriate instructions. Example in relation to the code asterisk. Let's go back to our C code example. As the compiler processes this code, the symbol table would be populated like this. 1. Global scope asterisk. Asterisk x, type, int, scope, global, value, 10, memory underscore address. Asterisk y, type, int, scope, global, value, 20, memory underscore address. Asterisk add, type, function, scope, global, return underscore type, int, parameters, int, a, int, b, memory underscore address. Asterisk main, type, function, scope, global, return underscore type, int, parameters, memory underscore address. Asterisk printf, type, function, scope, global, return underscore type, int, parameters, string, format, memory underscore address, assuming printf is treated as a built-in function. 2. Scope of add function asterisk. Asterisk a, type, int, scope, local, memory underscore address. Asterisk b, type, int, scope, local, memory underscore address. 3. Scope of main function asterisk. Asterisk result, type, int, scope, local, memory underscore address. The compiler uses this information to Asterisk type check asterisk verify that the add function is called with the correct number and types of arguments, 2 int arguments. Asterisk scope resolution asterisk find the definitions of x and y when calling add, x, y. Asterisk code generation asterisk generate instructions to access the values of x and y from memory and pass them as arguments to the add function. Then it can use the symbol table to generate the correct instruction for returning the sum a plus b. It also helps to allocate memory for result and store the result of the add function in its appropriate memory location. Important considerations. Asterisk error handling asterisk the symbol table is essential for detecting errors such as asterisk undeclared variables asterisk using a variable before it is declared. Asterisk redeclaration of variables asterisk declaring the same variable multiple times in the same scope. Asterisk type errors asterisk using a variable in a way that is incompatible with its type. Asterisk memory management asterisk for compiled languages, the symbol table helps with memory allocation and deal location. Asterisk complex languages asterisk modern programming languages, example C++, Java, Python, have complex features like classes, inheritance, namespaces, and modules. The symbol table implementation needs to be more sophisticated to handle these features correctly. Asterisk dynamic languages asterisk in dynamic languages, example Python, JavaScript, the types of variables might not be known until runtime. The symbol table might store less type information during compilation and more information at runtime. In summary, the symbol table is a foundational data structure in language processing. It provides a central repository for information about the identifiers used in a program, which is crucial for semantic analysis, code generation, and error detection. The choice of data structure for the symbol table depends on the specific requirements of the language and the compiler being developed. Understanding the role and implementation of symbol tables is essential for anyone working on compilers, interpreters, or other language processing tools.